Good evening, everybody. My name is Nicolas Rinaudo, and I'm the CTO of a Swedish company called Bisido, where we do a lot of online content moderation and machine learning. And tonight, I would like to talk to you about recursion schemes. Not necessarily so that you learn about them, although that would be a nice side effect, but it's more of a revenge story, really, because when we learn functional programming, when I was learning functional programming a few years ago, you know how hard it can get in the beginning. You have so many new things to learn and so many old things to unlearn, but there eventually comes a point where you finally get the impression that you don't know everything you need to know, but you know enough to start writing code that you don't have to feel ashamed about. And it's a very pleasant place to reach when you finally get there. But unfortunately for me, it lasted about 5 seconds before a friend of mine asked me, but Nicholas, do you know about recursion schemes? And unfortunately, I had to answer that I didn't even understand all the words in that sentence. So I had to get back to the books, read some papers, some videos, some blog posts to try and understand recursion schemes. And I reached a rather disappointing conclusion. My first take was recursion schemes are really rubbish. They're really very pretentious, very hard to put together, and for a benefit that's not quite clear, because the usual pitch goes something like, if you want to write an interpreter for a simple mathematical language, then doing it via recursion schemes is almost as good as doing it without. And I didn't feel that was a great sales pitch. So I went back to my friend and shared that conclusion. But he answered, but you don't understand, Nicholas. You can't be a proper functional programmer unless you know recursion schemes. And that was a bit of a low blow, because I dearly want to be a proper functional programmer. So I went back to the books, studied some more, and I realized after a while that the problem was not with recursion schemes, but that I just couldn't understand the way they were being taught. Because all the material you can find online is going to be about the theory behind them, which is absolutely beautiful and elegant and everything, but also very hard to grasp when you don't actually know what it is you're trying to achieve. So once I managed to push through this, I decided, as a sort of vengeance, to write this talk, which is how I would have liked people to explain recursion schemes to me from the beginning. And my promise to you is that at the end of this talk, you will understand what recursion schemes are and why you might want to use them. And I will also have given you the tools you need to try and study the rest, because there's a lot of them. There's a lot of recursion schemes, and I'm going to present, depending on how much time I have, 1 to 3 of them. But there's a lot more than that. But I will give you the tools you need to study all of the rest. And with that, we can dive into the material proper. The first thing, though, before I can talk about recursion schemes, I need to talk about recursive data types. And you probably know what a recursive function is. A recursive function is a function that is defined in terms of itself. And a recursive data type is the same thing. It's a type that is defined in terms of itself. And the simplest such type that I could think of is the linked list, which proper functional programmers call a cons list, because it makes a lot more sense. And the linked list, a cons list, is composed either of a cons or nil, which means the empty list. And a cons is a value, the head, and a tail, a value, the head, or a tail, which is a reference to the rest of the list. And if that tail happens to be the empty list, then you're done. You have gone through the entire list. And this can easily be encoded in Scala with a sum type list, which is either a cons or nil. And if you have a cons, it's composed of a head and a tail. As you can see, this list is not even polymorphic. It just contains ints, because it makes things simpler, and the entire purpose of the talk is going to generalize that as far as possible. So I felt it's easier to start from the simplest possible type to reason about, and then we get a lot of properties for free for much more complicated types. So that's our list. You can even create values of list. It's a bit noisy. You can see the list here, the values in your list here, but creating values of recursive data types is always a bit of a problem. It's always a bit cumbersome. So this is what we have. It's not great, but it's what we have. And now that we have a recursive data type, we need to work with it. And intuitively, you're going to think, Well, we have something recursive, we have a type that's recursive, so probably we're going to be using recursion to work with it. Of course, this is what we're going to be doing. And we're going to study structural recursion, one of the most common ways of working with recursive data types. And the way it works is you let the structure of your type guide the recursion. So, for example, you might want to compute the product of a list. Here's the implementation. You take a list of integers, values, and you return its product as an int. And this goes, as I said, we follow the structure of your list. So we pattern match on the list. And if we have a cons, which is the case here, we take the head, 3, which we multiply by the product of the tail. Back to the pattern match, we have another cons. So you take the head, 2, which is multiplied by the product of the tail. The tail is now cons, the head, sorry, is now cons with a head of 1, which is multiplied by the product of the tail, which is nil. So now you multiply that by 1, which gets us product of int is 3 times 2 times 1 times 1, which is exactly what I wanted to have, 6. So that's pretty nice. We have done product, but if you look at it from a slightly higher perspective, you can see a pattern. The first thing you do is you look at the simplest possible problem, the empty list. There cannot be any smaller list than the empty list, and you provide a solution for that. And then you look at a larger list, which is defined as a value and a smaller list. And then you provide a solution by relying on the smaller list, the solution of the smaller list, which you update with the additional value that you had. And we can use that same pattern to compute lots of things, for example, the textual representation of a list. So you take a list and you return its string representation by looking at the smallest possible list and saying that the solution for that one is a string nil. And the solution for a larger list is the head of the list concatenated with cons, concatenated with a string representation of the tail. And that, of course, yields exactly the result that we'd want. 3 cons, 2 cons, 1 cons nil. So what's structural recursion? Structural recursion, it works by providing a solution for the smallest possible problem. And then for larger problems, you rely on the solution to smaller problems and you compute the result of the larger problems based on that. And if that reminds you of proof by induction, this is, of course, not at all a coincidence. Before I go any further, do we have any questions so far? I can't actually see the chat here, so if there's any question popping in the chat, I can't see them. I will take that as a no. Right. So we have looked at structural recursion and seen that it was useful and handy to work with lists, but we had to rewrite everything from scratch every single time. What I would like to do now is generalize our structural recursion to have something that can be reused so that we can only plug the bits that are different. We're going to generalize structural recursion. And in order to do that, what we'll do is we'll start from mkstring and we'll refactor it all the way to something more general. So the first step is going to be renaming it to something, I'll call it recurse. It's not a great name, but at the moment we don't yet know exactly what we're going to end up with and how it's going to work. And I find that giving a name to something just when you write it is the worst possible time because you don't have enough information to know how to call it properly. So we'll call it recurse for the moment, and then later, when we understand better, we'll give it a better name. So this is recurse. We have, of course, not broken anything yet. We've just renamed it. And if you look at recurse as a diagram, the way it works is you take a list and you follow its structure to get either a head and a tail or not. Then you recurse on that head and tail to get a head and a string, the string representation of the tail. And then you use some hard-coded magic to get a string. And the first thing that I want to fix is that hard-coded magic. And the first step is going to be to get rid of the nil string, which is here in our code. So we just have this hard-coded string, which you can extract to a constant, which I'm going to call base, because that's the base case, the case for the smallest possible step of the recursion. And now I can get rid of the hard-coded string and replace it with a constant. It's not perfect yet. It's better to make that a parameter. And of course, we must not forget to update the call to recurse. And we still get exactly the same result as before. And in terms of diagram, we've replaced that hard-coded string with a parameter. So that's a good step forward. But we still have this, I don't even know how to pronounce that. Let's just call it cons, that we want to get rid of. And if you look at that, it's really just a function that you apply to the head of the cons and the result of recurse on the tail. So we can extract that into a function, which I'm going to call step, the step case. And we can replace this entire bit of code by a call to step. And as before, we're going to make step into a parameter, and we should not forget to update the call to recurse. Then again, we get exactly the same result as before, but we have something more general. In terms of diagram, we have replaced this nasty thing by a function called step, and we're pretty much done, at least at the term level, because now everything's parametric. But we still have the return type string hard-coded, and we know this is not the only type that we want to handle, because product, for example, returns an int. So we want to abstract over that. But luckily, if you look at the code, we never use the fact that we're working with a string. We need it to be a type, and we need it to be the same type everywhere it's highlighted. But we don't need to know it's a string. We don't really care about that. So we can just create a new type parameter and replace string by that type parameter without changing the meaning of our code. It's more general, but still doing the same thing. In terms of diagram, it means we have gotten rid of string here, and we get a diagram that is pretty close to what we want to express structural recursion in a more generalized way. I'm going to keep working on it a little bit, because there's a few things that I don't like about this implementation. The first thing is this call to recurse here. It's a bit nasty. It takes a lot of parameters. It kind of obscures the meaning of this bit of code. And it's especially frustrating when base is already in scope, step is already in scope. You shouldn't have to pass that. So what I'm going to do, it's a pattern that I do quite a bit. Not everybody likes it, but I do, and this is my talk, so we'll be doing it my way, is to take this pattern match and turn it into an internal function, which is usually called loop or go. I've gone for loop here. That's exactly the same code, which allows us to just apply it to the input. And now, step and base are in scope. So I don't need to specify them to loop. And this makes the intent of the code a lot clearer, at least in my opinion, because now I can tell that we're calling step on the head and the recursion, the result of the problem for the tail. And of course, this was just internal refactoring. We haven't broken anything. So in terms of diagram, the only thing we've changed is recurse is now called loop. And this is the final diagram for our recurse function. But there's another thing that bothers me here. Recurse takes a list parameter, values, but all it does is pass it to loop. And I don't really like that. I would prefer to just return loop instead. And of course, we need to fix the return type to be a function from list to A. And that yields exactly the same thing. Now, you might wonder, why have we done that? Because it makes the call site slightly weirder. We used to have a single list of parameters, and now we have two. It's not massively more complicated, but it is clearly a little bit more complicated. But the reason we've done that is because most of the time, you're not going to call recurse directly. You're going to use it to write combinators. mkstring, for example. This is how you'd express it. But you could also simplify it by saying that it doesn't take lists. It's a function from list to string. And then you can even make it into a val. And I feel that this way of writing mkstring is much more clear, because it's just telling you mkstring is a special version of recurse for this base and this step. So I like that part a bit better. And of course, now that we're done with recurse, we have to find a proper name for it. And some of you might already know the name. It's one of the few names that I actually find beautiful and useful in functional programming, because it's called fold, and it's very poetic, isn't it? Because you have a list, and you fold it onto itself bit by bit until you get a single value in the end. So I find that name quite nice. Now, I've shown you that you could express mkstring in tenfold, because that's what we've been doing so far. But what about product? Well, product can, of course, also be expressed as a fold. With a base case of 1, and a step case of head multiplied by the product of the tail. So that worked out. And of course, we get exactly the same result as before, the result that we wanted. So what have we learned? We've learned, not terribly surprisingly, that structural recursion is generalized by parameterizing the base case and a step case. But also, importantly, by knowing the structure of your type. We have generalized structural recursion, but for lists only, haven't we? And wouldn't it be nicer if we could find a kind of type that, under some constraints, we could write a version of fold that works for any types that follow these constraints. So that's what we're going to be working on. We're going to try and generalize folds. And again, it's going to be an exercise in refactoring. Take fold, which works, as I said, as this diagram. And if you look at it, the first bit where we have some information about list is right here. We have the structure of the list hard-coded. We take a list and we follow its structure. We have either a const or a nil. But if you think about it in a certain way, a const is a head and a tail, and a nil isn't. So you either have a head and a tail, or you don't. Which we already have a type for that in Scala. It's called option, right? Option is used to encode the possible absence of something. So we could rewrite this const and nil as an option, as sum and a none. But in order to do that, I need to be able to turn a list into an option of head and tail. This is traditionally done by a function called project. And it's very simple. If you have a const of head and tail, you return a sum of head and tail. And if you have a nil, you return a none. This allows us to use project to turn state into a sum and a none. And of course, project needs to be a parameter to our fold. And we still get exactly the same result as before. So in terms of diagram, we've turned this into this, which doesn't appear much better. This looks more complex, and it will get worse before it gets better, but it will get quite a bit better. But this at least abstracts somewhat over the notion of the structure of a list. An option of head-tail is very much a list still, but it's at least using a type, a different type than list, so maybe we can use that and bit by bit take away all the stuff that is list specific. And what we've done here is we've added a new type, option of head-tail. And when you add a new type to an algorithm, it's always a very good idea to look at the rest of your algorithm and to see whether this type appears somewhere else. Because if it does, then maybe you can reuse it, and maybe you found a new pattern that you can use to abstract over things or remove code duplication, these kind of things. So let's try to do that. Do we have an option of head-tail anywhere else in our diagram? Well, if you look at it in a certain way, here, step is a function from a head and a tail to an A, or from nothing to and base is a function from nothing to an A. So you could see step and base as two halves of a single function from an optional head-tail to an A. Let's try to write that. We should be able to combine base and step into something that I'm going to call up, because I'm really very bad at names, and we're going to be renaming that very soon anyway. And up is very straightforward. If you have a sum, so a head and the result on the tail of the list, then you call step. And we know that for nk string, step is a concatenation with const. And if you have none, then you return the base case. And we know that for nk string, the base case is a string nil. This is our up function, which we can now use it for. We can replace base and step by up. And of course, step becomes up of sum, and base up of none. So, and of course, we still get the same result as before. In terms of diagram, well, it's not very satisfying. We have two up arrows. I would much prefer to have a single one, but if you look at the code, luckily, up is called on both, on the right-hand side of all of the branches of a pattern match, which means we can take it out of the pattern match and apply it to the result of the pattern match without changing anything, which allows us to rewrite the diagram like this. And I did tell you it was going to get worse, but this is as bad as it gets. Now we're going to start simplifying. Because, well, this is our current diagram, and if you look at it, this option of head tail, I keep calling it option of head tail. That's not quite right, is it? Because on the left-hand side, option of int list, that's definitely an option of head tail. But on the right-hand side, we don't have the tail. We have a, in the case of mk string, a string. So we have the result of our recursive function applied to the tail of the list. And if you think about it that way, this is very much a representation of different steps of a structured recursion. On the left-hand side, we have an optional head and tail. So it's either none, so we have the smallest possible problem, the empty problem, or sum of a head and a tail, so sum of the smaller problem and whatever additional value we have to make it a bigger problem. But option of int a is, again, either none, we don't have anything to work with, we have the smallest possible problem, or we have a sum of the head and the solution to the smaller problem. And this makes it into a very interesting type. So interesting, in fact, that we're going to name it. I'm going to name it listf. That name is a bit rubbish, but there's a reason for it. List is clear. I mean, this is supposed to represent the structure of a list, so you stick list in the name. F, I don't want to explain just now, because it would spoil a surprise that I have in store for you a bit later. It's not a great surprise. It's not like I brought cake or anything, but if you already know where this is headed, it should be a nice surprise later. And listf of a is an option of a head and an a. And we have basically two versions of listf. We have the one that we use in project, where that type parameter is list. So in the case of a projection, we turn our list into a head and a tail. That's the structure of the list. But in the case of op, we have a string. We don't have a tail, we have the solution of the problem for the tail of the list. Right, so now that we have this type, we can replace option of int a everywhere by listf without changing anything. And in terms of diagram, we have this, which is not great yet, but at least going in the right direction. But now if you look at that center part here, it looks messy, it looks like a lot is going on, but you go from a listf of list to a listf of a by applying this bit, which really is essentially loop. And loop is a type from list to a. So you go from a listf of list to a listf of a by applying a function from list to a. That's a pattern that's beginning to emerge here. But just to make it absolutely clear what that pattern is, take this pattern match and extract it. In the first branch, if you have a sum of head tail, then you return a sum of head and a function applied to the tail. In the case of none, you leave it alone. This should really start to feel familiar. But to make it even more clear, take this entire pattern match and extract it into a function. I've already used loop, so now let's call it go. And it's exactly this pattern match as before, which we can just apply in loop. And now, look at go. It takes a listf of list, returns a listf of a by applying loop, which is a function from list to a. But let's make it even more clear. Let's get rid of loop. Let's create a new parameter, f, which is a list to a, replace loop by f, and of course, pass loop to go. And now go is a function that, given a listf of list and a function from list to a, gives you a listf of a. And that is map that you must have already used. You must have, it's everywhere. If you have an option of a and a function from a to b, you get an option of b. If you have a list of a and a function from a to b, you get a list of b. If you have a future of a and a function from a to b, you get a future of b. It's absolutely everywhere. It's so common, it's so prevalent, absolutely everywhere, that we even have a name for it. That's called a functor. And if we can somehow express our problem in terms of functor, then maybe we can start getting rid of some of that list structures that's been bothering us. So we're going to have to define functors, and there's many encodings that we could use for functors. Initially, I wanted to use subtyping, because it would work perfectly and be a little bit fun. But I didn't want to completely ruin whatever reputation I have, so we're going to do it the old-fashioned, boring way. We're going to use a type class. This is functor. A functor takes a type parameter, which happens to be type constructor, and exposes a function map that, given an f of a and a function from a to b, yields an f of b. That's all the functor is. Now, there's some additional constraints on it, but essentially means map must be sane. So, right, functor has a function map. Now that we have functor, we need to provide an instance of it for listf, a functor of listf, which is exactly the pattern match we had in Go. I just copied and pasted that. And what that says is, if we have a sum, then we return a sum where we apply f to the tail. And if we have none, we leave it alone. And that's our functor for listf. Now, just a little bit of boilerplate so that we make the code later a bit clearer. I'm going to create this map function, which takes an f of a, an a to b, and an implicit functor of f, and puts everything together so we don't have to do that manually later. And now that we have all these tools, we can replace that pattern match, that entire pattern match, by just a map, because this is exactly what we wrote. We wrote that map function to be the pattern match. In fact, Go is so much map that we can just get rid of it. We can just call map instead and remove the code of Go. And that code got a lot simpler, but still works exactly as before. And the diagram is now very simple, isn't it? We're not quite done. We still have listf that appears in there, and listf is exactly the structure of a list. It's an optional head and tail. That is a list. We'd like to abstract over that. But that's going to be very easy, because if you look at the code, the only thing we need to know about listf is that you can call map on it. So what does that mean? It just means that listf must have a functor instance. We could turn that into a type parameter. A functor instance means that f must be a type constructor, and that it must have a functor instance. Now that we have f, we can replace listf by f absolutely everywhere, and not at all change the meaning of our code. So in terms of diagram, we now have f here, but we still have list, the input type. But that's actually not a problem at all, because if you look at the code, you don't need to know anything about list. The only thing you need is a function that projects list into an f. But you don't need that to be list. It can be any type b, and we could rename list to b, and that would work just as well. And that would give us this new diagram where everything is absolutely generic. We don't have anything specific to list at all in there. So we appear to have a solution, but now we must find a name for it, don't we? Clearly it's not going to be fold, because it's a more generic kind of fold. And this has got a name that can be very intimidating. It's called a catamorphism, or kata for short. Now, this is not a name that seems very pleasant. But if you know the etymology for it, then it's actually very easy to remember. Kata means I know ancient Greek. Morphism means I know category theory. So catamorphism means I know more than you do. And this is what catamorphism means. Up is of course not called up. This has the name of the most overloaded term in functional programming. This is called an algebra, like just about everything else. And of course that f has actually got a useful name. It's called a pattern functor or a base functor, depending on the papers you read. And that's why, of course, listf had an f in the end, because of the functor instance. And really, I must insist, this pattern functor thing is extremely important, because you use it to abstract over the recursive part of your type. When we have a listf of list, then list represents the recursive part of the list. But when you have a listf of A represents the solution of a problem for the recursive part of the list. It's a very useful type. Right, so we have catamorphisms, and of course we must update the diagram because up is now called algebra. And this is the final diagram for kata. And, well, we have seen that kata worked for MK string because that's what we've been doing all along. But does it work for product? Of course it does. That's the entire point of the exercise. We need to provide an algebra for product, which simply maps sum of head and tail product to the product of the head and its tail, and none to 1. This is what we wrote initially when we wrote product. Now, product is a simple application of kata to the right algebraic projection. And of course, it still yields 6. So, what have we learned? We've learned that catamorphisms are structural recursion for types that can be projected into pattern functors. They're also far less complicated than their names make them out to be. And they're really just a simple refactoring away from the familiar fold. Once you had the intuition for the pattern functor, once you realize that a functor is hiding somewhere in there, the rest is fairly straightforward. But the thing is, here, I've told you that works for any type that can be projected into the pattern functor. But I've only showed you one. So it seems logical that it works, but if I were you, I wouldn't believe myself. I would prefer to see another type for which it works. So we are going to be working a little bit with trees. Here's a binary tree, which can be either a node, an empty tree, or a leaf, an empty tree. And if you have a node, it's composed of a value, a left branch, which is a reference to the left subpart of the tree, and a right branch, which is a reference to the right subtree. And if that happens to be the empty tree, then you're done, that path is finished. This is easily implemented in Scala, some type called tree, which can either be a node or a leaf. And if you have a node, it's composed of a value, a left branch, and a right branch. You can even create values of it. Again, creating values of a recursive data type is never very pleasant, but if you kind of squint, you can see the values that we put in the tree here. And, well, the problem that we're going to try to solve now is the height of the tree. The height of a tree is defined as the longest path from the root of the tree to a non-leaf node. And in that case, that happens to be 3. And of course, we're going to try to solve that problem with a catamorphism. This, sorry. We're going to be doing exactly the opposite as we've done before. Before we were trying to take the specific implementation and make absolutely everything generic. Now we're going to go from the generic implementation of catamorphism and try to make it specific to tree to make sure it works. So this is what we have. And we want to put concrete types everywhere here. So the first thing, B, the input type. Clearly that's going to be a tree. I'm sorry, I'm hearing a little bit of noise. Is this still working? I always worry that I kind of lose the...
We're still hearing you.
Oh, sorry. Sorry about that. I just had some weird noises. So let's get going. Tree. So we know that the input type is tree. But then once we have tree, we need to think about the pattern functor, F. I could do what we did before, which is use an optional value, left branch and right branch. But I don't really want to do that because tuples, there are parentheses everywhere. And I know that some of us really enjoy Lisp, but it just confuses me, and I don't really like working with all these parentheses and the _1, _2. It just makes the code confusing. So instead, I'm going to show you another mechanism for, given a type, a recursive data type, very mechanically derive its pattern functor. The first step is fairly straightforward. Take your type and add f in the end. Take the branches of your type and add f in the end, so we get node f and leaf f. Done. That was part 1. Part 2, the pattern functor has got to have a functor instance, so it has to have a type parameter. And of course, node f also must have a type parameter. And if you remember, the type parameter of your pattern functor is used to represent the recursive part of your type. For list, for example, the type parameter of list f was the tail of the list, it was list. So here, this A represents the recursive part of a tree, the left and right subbranches. And leaf f, of course, is also a tree f of something. But a tree f of what? When in Scala we have a type, we can use the universal subtype, nothing. But in order for that to compile, we have to make tree f covariant on A. If that didn't make any sense to you, you can absolutely think of that as a syntactical trick to get this whole thing to compile, because that really is all it is. And this is our pattern functor. So we could replace f by tree f, because we actually know what that is now. And now that we have tree and tree f, we need to be able to go from one to the other. We need to write the projection function. And the projection function is trajectory, which maps a node to a node f and leaf to a leaf f. It looks like it should be possible to derive that automatically, but here at least we're doing it by hand. Project is now trajectory, and in order to call map, we must make tree f a functor somehow. And this is actually fairly straightforward. Again, we have a functor of tree f, where the map method simply takes a node f, and applies f to the left and right subbranches, to the recursive part of the tree. And it just leaves leaf f below. Right, we have tree f, functor of tree f, so we're done here, and we can finally tackle the problem. The only bit that's actually of any interest in all that we've done, we wanted to compute the height of a tree, we had to do all this work first, but now finally we get to solve it by providing an algebra for the height of a tree, which is not very complicated and a bit fun to write, because height algebra, given a node, remember when we work with node f here in the algebra, we have the solution to the smallest part of the problem. So this gives us the height of the left subtree and the height of the right subtree. So the height of our tree is going to be 1, because we have to count the new node, plus the biggest of the left and right subtrees. In the case of a leaf, leaves are not part of the path of the height, so we don't count them and we just return 0. And now algebra is height algebra, and we're done. We have done everything we needed for computing the height of a tree as a catamorphism. And height is expressed as a catamorphism with the right algebra projection, and it yields 3, which is exactly what we wanted to see. So that's perfect. We have managed to write the height of a tree with catamorphism. That did involve a lot of busy work though, didn't it? We had to do a lot of things. We had to define the type, the pattern functor for the type, the functor for that pattern functor, the projection, and finally we got to the algebra. Now, we have a choice. I can stop here on this cliffhanger. This is the conference version of the talk, where I have 45 minutes, so this is where I have to stop. But I could also show you how to reduce the boilerplates that I've just talked about, which is actually kind of fun. Or I could show you another recursive pattern, generative recursion, to show you different ways of working with recursion schemes. This is up to you. You just tell me what you want me to do, and we'll do that. Utter and complete silence. I'm going to take that. Yes?
So I could choose, but I think that let's wait a few minutes, well, not minutes, but a few moments
Sure.
for anybody to ask in the chat what they want. So we've got some interest in reducing boilerplate, and actually that's something that I'm really interested in seeing as well.
Okay, let's do that then. Right, so as I just said, the problem with catamorphisms was that before we can actually use them, we need to do a lot of groundwork. We have to define a type, a pattern functor for the type, a projection from one to the other, a functor instance, and then finally we can start doing interesting things. It would be a lot nicer if we could not have to do that. And the intuition we're going to follow here is that if you think about the pattern functor, say list f, a list f of list is very much a list. It's a structure of a list. It's got a tail that's a list. It's an optional head and tail. It's exactly a list. So maybe we could find a way of expressing a recursive data type in terms of its pattern functor. So that way we would only need to implement the pattern functor and not the type itself. So that's a lot less copy and pasting. And possibly the projection from one to the other could be either free or easier because it's all based on pattern functor. So what we're going to try to do is to express lists in terms of list f. I'm going to call that type list2 because, well, first, I'm not very good with names, and second, it's kind of a list, but it's not our list type, so it's just a second list. there's got to be a list f of something. But list f of what? If you remember, list f represented the recursive part of our data type. So the tail, and the tail of list 2, the tail of a list is a list, so the tail of a list 2 has got to be a list 2. So what we want to do is that. We want list 2 to be a list f of list 2. But unfortunately, that's not going to work, because Scala does not allow recursive type aliases. But we have been working with recursive data types for the past 45 minutes. So maybe we can't use a recursive type alias, but maybe we can use a recursive type. Maybe if list 2 cannot be a list f of list 2, it can contain one. Now, that type is deceptively simple, but whenever I try to understand it, it kind of does my head in a little bit. When that happens, what I do is I draw things until it makes sense. So let's try that here. Let's create int2, which is our list from before, 3, 2, 1, but expressed as a list f. Right, so we want to create a list2. What's a list2? List2 is a wrapper for a value of type list f of list2. List f of list2, if you remember, it's an optional head and tail, and here we want to have a head because we want 3, 2, 1. So we want a sum of 3 and a tail of type list2. A list2 is a wrapper for something of type list f of list2. List f of list2 is either a head and tail or not, and here we want to have a head because we want to have 2. So we have a sum of 2 and a tail of type list2. List2 is, again, a wrapper for something of type, for a value of type list f of list2. Again, we want to have a head, so we get list f of list2 is the sum of 1 and a tail, which in that case is again a list2, which is a wrapper, almost done here, which is a wrapper for something of type list f of list2. And we have reached the end of the list here. So we're just going to return now. Now, if you look at that diagram, you can see that the list is still here. We can see here sum 3, sum 2, sum 1, none. And in the diagram, you can see it. But you also have list 2 here, which is inserted between every single element of a list. But that's an important observation, because the structure of list 2 is encoded by list f. Not at all by this list 2 here. The structure of the list is in the list f. List 2 is just data, structure that we add to appease the compiler and to make the data type recursive. But if list 2 doesn't actually represent the structure of the type it's wrapping, then maybe we could use list 2, or the same trick as we used for list 2, to represent other recursive data types. Say tree. Tree2 contains a value that's of type treef of tree2. And that's very much list 2. It looks a lot like it. It's got a different name, but that's easily fixed. And of course, it uses treef instead of listf, but maybe we can do something about that. So let's go back to list 2, and let's make listf into a type parameter. Listf is a type constructor, so it's got to be a type constructor in the type parameter, and listf is now an f. And list2, of course, takes type parameter now, which has got to be f. And we get list2, which this type is a little bit complicated, and it's got a name that makes it even worse. It's called fix. But there is a very good reason for why it's called fix, and I actually find that quite fun. See, let's look at it from the mathematical definition of what fix is. Fix is called the fixed point combinator. The fixed point of the function, so given a function f, the fixed point of that function is x, such as f of x is equal to x. And the fixed point combinator, fix, is a function that, given a function, returns its fixed point. So fix of f is equal to x. Let's rework that a bit. We know that x is equal to f of x. So we can replace that x by f of x. But we also know that x is fix of f. So we can replace that x by fix of f. And now, if you look at the code and the last equation, we have written exactly the same thing. Fix of f maps to f of fix of f. This is why this is called the fixed point combinator. Now, we have the fixed point combinator, which we can use to express any recursive data type. Fixed list, least expressed in terms of its pattern functor, is fixed of list of f. We can even create values of it. The signal to noise ratio is not great. This is a signal, this is a noise. Not necessarily amazing, but at least it works. It could be worse. We could be doing trees. Fixed tree is a fix of tree. Sorry, fix of tree f. And you could create values. It's a lot of code to just put 4 values, isn't it? But that's how a tree works. So how a fix works. Right. So now we know how to express a type, a recursive type, in terms of its pattern functor. So what has that earned us? Well, let's see. We can try to specialize kata to only work with data types that have been expressed in terms of the pattern functor. So kata, well, we're going to rename it, right? It's a specialized version of kata, so we're going to call it kata fix. And if you look at the diagram, we know now that B is going to be expressed in terms of its pattern functor. It's going to be a fix of its pattern functor, this B. So we can get rid of that type parameter and replace it with fix of f. And that still works as before. We now have fix of f, and this slightly mystical f of fix of f in the middle. Hard to reason about the f of fix of f. Whenever I see that type, it's kind of a weird type, but we know how we got there, and we know it made sense, so let's trust that it works. But now we want to be able to project from fix of f to f of fix of f. And there's 2 ways we could go about that. There's the usual statically typed functional programming language gimmick of saying, well, there's only really one way I can get this to compile by following the types, so that's what I'll do. And if we did that, we'd get to the answer in a flash. But the cost of that, though, is the only reason you have for knowing this works. The only understanding that you have is, my magical friend, the compiler, told me it worked. But you still don't know why it works, just the compiler told you. So instead, we're going to go the long way around and reach the same conclusion, but hopefully along the way, you will have understood how we got there. The way we'll do it is, as always, you refactor things. So you take project, which is how we projected a list into a list f, rename it to project fix, of course, and now start refactoring. We know we're not working with list, we're working with fixed list, and we know fixed list is actually fix of list f. Now, if we have a fix of list f, then cons, we know, is actually represented by fix of sum, and nil is represented by fix of none. Done. But if you look at that pattern match, in the case of sum, you just take the sum out of the fix and return that. And in the case of none, you just take the none out of the fix and return that. So we could replace that entire pattern match by returning the value inside of the fix. And that is all that is. But of course, this is still hard-coded to list f. And it really doesn't need to be, does it? We could turn list f into a type parameter. First, of course, we need project fix to be a def in order to be able to have type parameters. And then, given a type constructor f, we can replace list f by that type constructor without changing the meaning of project fix, which allows us to rewrite catafix, because now that we know that for any type expressed as its pattern functor, the projection is just retrieving the value, we can get rid of project, just called value instead, and get rid of project in the parameters because we don't need it at all. Project is now simply retrieving the value, and now things start to get a bit easier because, well, we're not using our initial type anymore, we are working with a pattern functor, so we already have a functor instance here because we have already provided a functor for the pattern functors. We have provided a functor instance for list f and tree f. By definition of a pattern functor, you already have a functor. So this is done. In the algebra, again, we have already provided it, tree height, or product algebra, all these things. We can still use them because we're still working with the same types. Product fix, for example, which is a function from fixed list to int, is just catafix of the algebra we already defined, and that works. The same goes for height. The height of fixed tree is just catafix applied to the height algebra. Now, this has made our life slightly simpler. We only had to define the pattern functor, not the type itself. So that's a bit of copy-pasting we don't have to do. We have removed the need for projection. We got that for free. And also, we have made the act of coding kata slightly simpler because we don't have to explicitly pass the projection. So that's sort of nicer. But there's a cost, of course. If you want a pattern match on the list, now this is what you have to do. This is what we used to have to do. So it's a bit more complicated, and you have to know about a type that's a bit more complex than before. But it's not a massive problem. But and most people would argue, well, Nicolas, this is not very fair because catamorphisms have been designed so that you don't have to do explicit pattern matches. And I would argue that being able to do pattern match is still useful every once in a while. But let's pretend that this argument is workable, that I actually believe in it. What about creating values? I want you to create values. I have created a type. I would like you to create values because otherwise you're never going to use the type. What is even the point of me having done all that work? This is how you do it now. And this is how you used to do it. And even back then, when I first showed you how to create a list, I said, well, this is a bit noisy, but this is what we got. This is what we have now. It's far worse. Could be so much worse as well, because this is a list, it's not a tree. I would have used a tree here, but the code didn't even fit on the slide. So there is a cost to fix. And you have to see it from a certain perspective. Using fix makes the hard case easier. For me, from my perspective, as a data type author, I wrote a library with data types, and my life has been made slightly easier because I didn't have to write both the type and the pattern functor. But that would have happened exactly once, though. Just once across the whole lifetime of my type, I would have had to write the type and the pattern functor. I didn't have to write the projection, but again, write that once and it's done. And it's also making it slightly easier for me to call kata. But from the perspective of you, the users of my library, we have made the easy case harder. It's harder to pattern match and to create values. So from our perspective, using fix makes very little sense because it's exactly the wrong trade-off. If I write a library, I'm not writing it to push all the complexity of the problem I'm trying to solve onto you. I want to take that complexity for myself, and so that you don't have to, so that you only get to do the pleasant, easy thing. So I feel that fix, beautiful though it may be, and it's a very beautiful construct, in the context of recursion schemes, at least in Scala, doesn't make a lot of sense. And I think it's a shame that all the articles on the matter will always start with, right, before I can tell you about recursion schemes, I must tell you about fix, because it's absolutely critical to recursion schemes. It is not necessary, it's just a trick to reduce the boilerplate. And it's not necessary, and it's not even a good idea. So I would say, if you can, stay away from it, at least in the context of recursion schemes. And now you have another choice. We can stop here, or I can start talking about generative recursion, which there's a purpose behind that, because first I want to show you another design pattern, another recursion scheme, so that you can see that sticking a pattern functor in there is going to give us a solution very easily. And also it solves a problem that has been pestering us, which is creating values of recursive data types is not pleasant. But this takes about another half hour, I'd say. So I can keep talking or I can stop now. It's really up to you.
Once again, while I'm, of course, very, very happy to keep talking about recursion schemes, I'm going to just wait for a moment and see what anybody in the chat would actually like. But I suppose we can take a short interlude to say that I completely agree with you, by the way, Nicolas, especially about the way that fix is taught and the fixation, if you will, on fix. I think it detracts from a lot of the really beautiful ideas in recursion schemes.
Completely agree. But it is a fun type to work with, though. It's complicated, but at the same time, it does some really weird thing to types, and it's really very fun. But it's not important to understand recursion schemes, and recursion schemes are hard enough that you don't want to add that layer of complexity. At least in my opinion. I'm clearly not an expert, but this is what I feel.
Well, I think that one of the actually, why don't we save this discussion for later, because of course I can go on and on as well. So I think that a lot of people would quite like to hear about generative recursion. So let's keep going with that, and we'll discuss later as well.
Okay, right, let's do that. So generative recursion. We have seen that both for trees and lists, and even more so with fixed, creating values of recursive data types was problematic. It was noisy, it wasn't pleasant. Well, there's of course a way of working around that. It's a common recursive pattern that we can use. It's less common than structural recursion. Structural recursion is by far the most common recursive pattern. But generative recursion is a way of creating values of recursive data types from a single value. For example, you could create a range from an int. Given an upper bound, you could return a list of all of the integers from that upper bound to 0 excluded. And the way that would work is, first, we check. Is our upper bound greater than 0? And if it is, we return a cons, whose head is our upper bound, and whose tail is a range from the next integer. In that case, that's 2. Is 2 greater than 0? Yes, so we get a cons with a head of 2, and a tail of range of 1. 1 is greater than 0, so we get another cons, whose head is 1, and whose tail is range of 0. 0 is not greater than 0, so we get nil. And range of 3 then is a list 3 to 1, which is, of course, what we get when we call the function. But as before, there's a pattern here. We have a predicate. We evaluate that predicate, and if that holds, then we get a new, we create a new head for a list from the state that we were given, and we create a new seed, a new state from which to keep recursing, and we stick that into the cons. And if the pattern, if the predicate doesn't hold, then we get an error. And this pattern can be applied to many other problems. Another one we could do is, given a string, return its content as a list of bytes. You might, for example, want to write it to a row byte output string. So that would be called car codes, which, given a string, returns a list of its characters as ints. And the predicate is either string non-empty. The extraction of a new head from the state is just getting the first character of the string as an int. And the new state is the remainder of the list, which we stick into car codes, recurse over, and create a cons with. And of course, nil is the case for the empty string. And of course, if you call car codes on kata, for example, you get the expected result. Then we've seen that generative recursion then is composed of a predicate that is going to tell us whether or not we should keep recursing, and a way of extracting a value and a new state from a given state. And there's some recursive structure around this element. That recursive structure, I'd like to abstract it so that we can generalize generative recursion. We keep generalizing things. That's the entire purpose of what we do with recursion schemes. We take something simple and we generalize it, and generalize it a bit more, and then keep generalizing until we hit a wall. So let's keep generalizing here. We're going to generalize generative recursion. And that's going to be very similar to what we did before. Take car codes, rename it, because we're not working with car codes anymore. We're even going to use the same name, recurse. That's going to go slightly faster, because it's pretty much the same thing we've done before for fold. So we haven't broken anything yet. If you take the diagram, now this diagram is a bit nastier than we used to. But you go from a string, evaluate a predicate on it, which yields either true or false. And if it's true, then you extract a head and a tail from the string. And if it's false, you don't actually do anything. Then you get a head and a tail, which you recurse on, which gives you a new head and tail. And you use the structure of the list to turn that into an actual list. And the first thing we want to abstract over is a predicate. In the code, it's right here, and it's just a function from string to Boolean, right? So we can turn that into a function from string to Boolean, which I'll call predicate. And we can replace the call inside of recurse by that. And of course, predicate must be a parameter, and we must not forget to update recurse with that new parameter. And our code is now more generic, but we haven't changed its meaning. So in terms of diagram, we've made it slightly better, because we don't have a hard-coded predicate, but we still have a hard-coded extraction of a new value and a new state from a given state. So let's work on that. Here, what happens is, given a state from, we extract a new value and a new state. So that can be encoded as a function, which given a string returns a tuple in string, a head and a tail. And that allows us to replace that bit of code with something that's a bit more complex, but not that much, where we call update on our from, which yields the head and next state. We put the head at the head of a cons, the next state as the seed for the next step of the recursion, and that's the next step of the recursion, and now we can put update as a parameter, and let's not forget to update the call to recurse with that new parameter. And that gives us the same answer as before. And in terms of diagram, we've done that. So there's nothing hard-coded anymore, except maybe the type, string. But as before, if you look at the code, we don't actually need it to be a string. We need it to be coherent across all parameters, but we don't really care that it's a string. So we can just turn it into type parameter and replace string with that type parameter everywhere. And that hasn't changed anything to the behavior of our code and made this diagram more generic. And this is the final diagram for our recurse function. But exactly as before, we're going to clean it up a bit. Recurse is frustrating because we have to specify predicate and update, even though they're already in scope. So we're going to use the same trick. We're going to take that, turn it into a helper function called loop again. Recurse is just an application of loop, and predicate is now in scope, update is in scope. So we can call loop directly without all these parameters and express our recursive pattern much better, because now we know that we're creating cons from the new head and recursing on the new state. So this is better. We need to update the diagram because we're not recursing on recurse. Recurse is not recursive anymore, loop is. And this is our final diagram, but I'd still like to simplify it somewhat. Again, recurse is taking a from parameter, which we're just passing to loop. So instead, I want to return loop and update the return type of list of recurse to a function from A to list. And with that, I'm happy. We have a working recurse function, but we need to name it. And again, this is one of these actually beautiful names. You have fold, which takes a list and folds it onto itself to get a value. This does exactly the opposite. It takes a value and then folds it until we get a complete list. So this is called, very logically, unfold. And, well, we have seen that unfold worked for car codes, because this is how we write unfold. Does it work for, what was the other one? Range. Sure. Range is an unfold, where the predicate is our state greater than 0? And the update is the new value is a current state, and the next state is state -1. And that yields exactly the result that we had before. What have we learned? We've learned that generative recursion is generalized by parameterizing the predicate and the state update. But unfortunately, again, by knowing the structure of the type. And of course, you know where this is going, right? We are going to generalize unfolds. But we're going to cheat now. We know that pattern functors allow us to do recursive stuff much more cheaply and generically. So let's do that. Let's try and stick a pattern functor in there as soon as possible. Take unfold. If you look at the diagram, this bit looks a little bit messy, but you could see it as a function from an A to an optional head and A, right? Which is exactly what we want to do. We want to introduce listf of A in here, an optional head and a, that's a list of a. So let's do that. Let's see if we can turn predicate and update into a function from a to an option of head and tail, of head and a. I'm going to call it up again, because that kind of like the symmetry. And this works by, if the predicate holds, and we know the predicate in the case of card codes is the state non-empty. And if the predicate holds, then we return sum of update. And we know that in the case of card codes, the update is extracting the head of the string as an int and extracting the tail. And if the predicate doesn't hold, then we return none. And that gives us an optional int and string, which really everybody knows now that this is a list of string. This is our up, which we can now use in unfold. And well, that's going to take a little bit of refactoring, but not that much. What this is equivalent to is a pattern match on the state. And if we have a sum, so that means that the predicate has held, and we also get at the same time the new state and the new value, then we stick them into a const and recurse. And if the predicate hasn't held, then we return the empty list. And that still works. And in terms of diagram, we have simplified things a bit. Not that much, but a little bit. But more importantly, this diagram is starting to look a bit familiar, isn't it? Right, so we have put pattern functor in there. What about here? This also looks like a pattern functor of sorts, doesn't it? Because we have a head and a tail, or not, which we turn into a list. We have an optional head and tail, which we turn into a list. That definitely looks like a pattern functor. This is where that code lives here, and we would like to be able to, given either a const of a head and a tail or a nil, turn that into an optional head of tail. That should be fairly easy. It's traditionally called embed, and the way we do that is by turning a sum of head and tail into a const of head and tail, and a none into a nil. And of course, I'm not going to insult you. This is not an option, this is a list f. Right, so this is our embed function, which unfold is now going to take as a parameter. And this allows us to replace this bit of code. We're not working with a const, but we're working with an embed of sum. And we're not working with a nil, but with an embed of none. And as before, embed is being called on both the result of all the right-hand sides of the branches of a pattern match. So we can take it out and apply it to the result of the pattern match, which doesn't actually change anything in our code, but allows us to replace this diagram by that. And this is not great looking, but that bit here, that's exactly a functor, isn't it? We go from listf of a, apply loop, which is a function from a to list, and get a listf of list. That's functor all over again. So we can take that entire pattern match and replace, look, sum is just applying loop inside of the sum, and none is not doing anything. We can turn that whole thing into a call to map, which of course works, because we know this is going to work, and allows us to simplify the diagram quite a bit. And this is looking decidedly familiar. We still have listf. We want to get rid of that. But exactly as before, the only thing we need to know about listf is that we can call map on it. So we can replace that by a type constructor that has a functor instance, f, and get rid of the listfs without actually writing anything in the code. Diagram is slightly simpler, but we still have list to take care of. And again, as before, we don't actually need to know this is a list. We just need embed to work with it. So we could create a new type parameter, b, and replace list by b without actually changing anything in the code. Everything still works. But now we get a much better diagram that is completely generic, and that does unfold for any data type that can be projected into a pattern functor. Of course, we now need to name it. This is not called unfold. This is called an anamorphism, or ANA for short. But again, this is a very easy way to remember what it means. ANA means I know even more in generic than I did. Morphism, I still know category theory. Anamorphism, I do know quite a bit. Up, well, op's got a funny name, because if you look at the type of op, it's a function from A to f of A. And if you remember, we had a type that looked quite a bit like that before. It was a type of algebra, which was an f of A to an A. So exactly the same type, but you flip the arrow. The arrow from the function is going in a different direction. And people who study category theory, when they do that, when they have something and they change the arrows in there, they call the result a co-something. So we had an algebra. This is now called a co-algebra. Of course, we have just renamed a few things, so we haven't broken anything, and we can update our diagram to take a co-algebra rather than an op. And this is the final diagram for anamorphisms. And we know we can express car codes as an anamorphism because that's what we've been doing. What about range? Well, if we provide a co-algebra for range, which is fairly straightforward, our predicate is our current state greater than 0? Then if it is, we return the head, the new head, which is the current state, and the next state, which is -1. And otherwise, we return the empty list. Then range is just an application of anamorphism for the right coalgebra and embedding. And that yields the expected result, the list 3, 2, 1. What have we learned? Well, anamorphisms are generative recursion for types that can be embedded from a pattern factory. They're also far less complicated than the names make them out to be. And they are suspiciously similar to catamorphisms. Because they do look very samey, don't they? We have the same kind of vocabulary, the code looks similar, the diagrams are all about the same. So, well, let's study that similarity a little bit. Let's study generalized faults, or unfaults. Take this diagram. Can you tell me which is kata and which is ana? Well, we know that kata has an algebra, so this one must be kata. And ana has an algebra, a co-algebra, so this one must be ana. But they're really very similar, aren't they? It's hard at a glance to tell which is which. They're actually similar in two different ways. The first way is a lot more obvious. If I take the diagram for ana and flip it around, I just change the layout, not the meaning of the diagram, but just flip the nodes around. Same diagram is just going in the other direction. And now a pattern emerges, because if you look at this diagram, the nodes are exactly the same, but the arrows are going into different directions. And as we've just seen, when I said, well, if you flip the arrows, you call that co-something, and you call it a dual of something, this is what people mean when they say that a catamorphism and anamorphisms are duals of each other, because they're the same thing, but with arrows going in different directions. And the thing is, if you have arrows going in different directions, but they're the same thing, it means one ends where the other one begins, doesn't it? Anamorphisms end in B, and catamorphisms begin in B. We can probably compose them then, which gives us this diagram. What would be the point of composing them? Well, for example, you could express factorial as a composition of range. This gives us, range of 3 will give us 3, 2, 1. And with product, and product of 3, 2, 1 is 3 times 2 times 1, which is exactly factorial of 3. And of course, we get the expected result. Similarly, you could create a function called showRange, which, given an int, creates a range for that int and represents it as a string. So it creates a range of that int and represents it as a string, which of course gives us a list 3, cons 2, cons 1, cons nil. In terms of diagram, let's make that more concrete. Let's make that concrete to this code that I just wrote, show range. We know that the coalgebra is actually range of coalgebra for here because we're calling range, and we know that range takes an int. So we know that we can update the diagram like that. We know that f, in the case of range, there's got to be list f because range works with lists, so we need the pattern factor for lists, which is list f. So f must be list f. Then we know that B, range yields a list, so the output must be list. Similarly, we are now not doing range anymore. We have started working on mk string, and we know that mk string takes a list, so that B must be a list. We also know that MK string working with a list must use a pattern functor that is listf, so this f must be listf. And finally, we know that the A of MK string, so the output of MK string, is a string. So we know that we can replace that A by string and use the MK string algebra, which gives us this diagram. But if you look at this diagram, specifically at this part, it does look like we're doing too much work, doesn't it? We somehow eventually get to a listf of list, which we embed into a list, and then project back into a listf of list. It kind of looks like we're doing these two steps for nothing. But just to make sure that this intuition is correct, let's look at actual values, concrete values, to see whether we actually get the same values. Let's call show range of 3. So the first value that we have is the input type, int. It's 3. Then we have to call range coalgebra on that value. And range coalgebra tells us, given a state, 3, we compare it with 0. Is 3 greater than 0? Yes. Then we get a sum of 3 and recurse on 2. Is 2 greater than 0? Yes. So we get a sum of 2 and we recurse on 1. Is 1 greater than 0? Yes. So we get a sum of 1 and then we recurse on 0. 0 is not greater than 0, so we get none. At the end of that step, we get sum of 3, of sum of 2, of sum of 1, of none. Right, then we recurse. This is how we get to all the bottom of all these nested sum things. And we call embed. Embed is telling us to map all the sums to conses, all the nons to nils, and to leave the heads alone. And now we get this new cons of 3, cons of 2, of cons of 1, of nil, which is exactly a list, isn't it? Now that we have done that step, the next step is projection, project. Project tells us to map all the conses to sums, all the nils to nons, and to leave the heads alone. And finally, after we recurse a bit, we get to the algebra. An MK string algebra tells us to map all the sums to the application of step. And if you recall, step is head concatenated to cons concatenated to tail. Then we have to map all the nons to the base case, which in the case of MK string was the string nil. And finally, we leave the heads alone. And we're done. We get exactly what we wanted, 3 cons, 2 cons, 1 cons, nil. But these two steps are exactly the same. We don't need to do all that round tripping. This is just something that we can get rid of. We want to get rid of the embedding and the projection, because they serve no practical purpose. It just added computational time. So we don't want to do that. We want to get rid of them, of embed and project, and just do range coalgebra followed by MK string algebra. So this is a function that we want to have. We just want to apply range coalgebra followed by MK string algebra. First, what we'll do is we'll make that generic again. We'll go quickly this time. I'm not going to do any refactoring. I'll just stick the right types in. We know that we want an input type and we want a generic, so let's call it A. We know that we want listf to be a pattern functor, so let's call it F. And we know that we want an output type that is generic, so let's call it B. And finally, range coalgebra is going to be a coalgebra, and MK string algebra is going to be an algebra. Now, if you look at that function, at that diagram, I would like you to tell me how it differs from the diagram of Anna. This is our new function, this is Anna. This is our new function, this is Anna. There is a difference. The name of the last parameter is not embed, it's algebra now. Fair enough. Let's refactor Anna. Let's rename embed to Anna, to algebra, sorry. And that works. That's exactly the function we wanted. And if you don't believe me, let's call showRange, which is an Anna, on the range coalgebra and an MK string algebra, and that gives us 3 cons, 2 cons, 1 cons, nil. So this is exactly what we wanted. But, wow, we do love our names, don't we? So even though this is exactly Anna, it's got a name of itself. It's called a hylomorphism. You know the pattern, you know how to remember it now. But we have seen that a hylomorphism is exactly the same thing as an anamorphism. But now, a little bit of magic now. Take hylo, and now we're going to do some cosmetic refactoring. We're going to flip the A's and the B's. They're just random names. They don't actually mean anything. So we're just going to call all the A's B's and all the B's A's. Then I'm going to change the order of these two parameters. Start with algebra and finish with coalgebra. And then, just because I want to, I'm going to call coalgebra project. And now that I've done that, I would like you to tell me how that differs from kata. It's exactly the same thing, isn't it? If you don't believe me, go back through the slide and see I have actually copy-pasted the code for kata. So, Hylo is exactly an ana. Kata is exactly a Hylo. So by transitivity, kata and ana are the same thing. Which, well, it's a bit headache-inducing, isn't it? Because catamorphisms and anamorphisms, they're similar because they're duals of each other. They're exact opposites of each other. But they're also the same thing, which is kind of mind-numbing. And yes, it does give me headaches. But there is a reason for that. It's actually logical. It's just that the types that we've been using are a bit too weak. But the way you must think about that is that, yes, a catamorphism is a hylomorphism. The only difference is that catamorphisms take a projection where hylomorphisms take a coalgebra. But projection are coalgebras, but they're very specific kind of coalgebras. Projections are coalgebras that take a recursive data type and project it into a pattern function. All projections are coalgebras, but not all coalgebras are projections. So catamorphisms are very specialized kind of hylomorphisms that are used to go from a recursive data type to something else. And similarly, anamorphisms take an embedding, whereas hylomorphisms take an algebra. And exactly as for catamorphism, embeddings are algebras, but not all algebras are embeddings. So anamorphisms are just very specialized hylomorphisms that are used to go from one value and turn it into a recursive data type. And now, this is actually all I wanted to show you for tonight. Now, in closing, if you only remember one slide, this is where I point out that I delivered on my promise. I have shown you what recursion schemes were. They're just recursive design patterns for recursion. You take a common pattern, a common recursive pattern, structural recursion or generative recursion, and then you generalize it and you give it names so that everybody can recognize them. You give them patterns so that everybody can reuse them. These are exactly design patterns. So recursion schemes are design patterns for recursion. And now that you know about pattern functors, if you want to play with recursion schemes, if you want to see all the other ones, and the wealth of other ones, you can derive them by yourself very easily now that you know the trick of the pattern functor. Take a recursive pattern, force a pattern functor in there, and before too long, you'll get a proper recursion scheme. And now you have all the things you need to study them by yourself. And you can study all the really wild bits, how they talk with each other and how they compose together to give you some more interesting things. Do we have any questions?